I'm replacing the usual organizer who is moving in a new house today. Anyway, so it's a great pleasure to introduce today's speaker, who is Nicolina Istrati from Tel Aviv, and she will tell us about variational problems in conformal geometry. Please.
Okay. Hello, everybody, and thank you very much for the invitation to this seminar. So I will speak today about joint work with Daniele Angella, Alexandra Otiman, and Nicoletta Tardini concerning some special classes of almost Hermitian metrics and compact, almost complex manifolds, and their relation to some natural functionals. So the context we are is the following. X and J denotes an almost complex manifold, which is connected, and of real dimension bigger than 2. And G is a metric which is compatible with the almost complex structure. So this automatically defines a positive one-one form via this formula. And for the rest of the talk, I will just call omega a metric and completely identify it with J. And so since the real dimension is bigger than 1, the real dimension is bigger than 2, wedging with omega from 1 form to 3 forms is an injective morphism, and this gives us a splitting of the space of 3 forms into the image of wedging with omega and the space of primitive 3 forms. So in particular, d omega writes in a unique way as a 1 form wedge omega plus a primitive form. So primitive here means precisely lambda c is 0, where lambda is the adjoint of wedging with omega. And of course, when the metric is scalar, d omega is simply 0. But when the metric is not scalar, in general, we have an important invariant of the metric, which is determined by this one form. So in this talk, the Lie form of omega will in fact be n-1 times this theta. And it can be also equivalently defined as being, by this formula, as being J of the codifferential of omega. And in particular, omega satisfies also this equation, always. And so looking at the splitting of the omega, we have a few special classes of Hermitian or almost Hermitian metrics. So the first case is when the Lie form is 0. So this is equivalent to the omega, to the form omega being co-closed, and these are usually called balanced metric. The somewhat dual case is when the primitive form is 0. And then we also ask that the Lie form is closed, although in higher dimension, it is always closed as soon as the primitive form is 0. And this is what is usually called locally conformally scalar metric. A more general case than this is when we only ask for the Lie form to be closed, and this is called locally conformally balanced metric. And there is another notion of metric, but which has nothing to do with the splitting, which is the case when omega is DDC closed. And this is usually called either pluriclosed or strongly scalar with torsion. And note a few facts. So first of all, when the complex dimension is 2, the omega always writes as theta wedge omega because wedging with omega in this case is isomorphism. And so being balanced is the same as being scalar, and being locally conformally scalar is the same as being locally conformally balanced. And another remark is the fact that scalar and balanced are somehow similar notions in the sense that they both are unique in their conformal classes up to some constant multiple. On the other hand, locally conformally scalar and locally conformally balanced are conformally invariant notions and are in fact conformal generalizations of scalar and balanced. And this is precisely the case when the Lie form is closed. And the name also makes sense because the form is closed, locally it is exact. And then these two classes of metrics can always be locally made conformal to either a balanced metric or a scalar metric. And of course, there are important examples of all of them. I'll just give one for each. So balanced metrics exist on all modifications of Kähler manifolds. So as you might know, a modification of a Kähler manifold need not be Kähler. There are examples of Hironaka, of counterexamples of this. However, they always admit a balanced metric. For locally conformally Kähler metrics, Hopf manifolds admit such metrics, and in general, almost all complex surfaces, compact complex surfaces, admit locally conformally Kähler metrics. Locally conformally balanced, for example, blowdowns of locally conformally Kähler manifolds are locally conformally balanced. And finally, for pluriclosed metrics, all semi-simple compact Lie groups of even dimension admit pluriclosed metrics. And when looking at conformal classes of Hermitian metrics, there is another important notion of a metric, which is the Gauduchon metric. So a Gauduchon metric is an almost Hermitian metric, which is defined by the condition that the Lie form is co-closed, or equivalently by the fact that omega to the power n minus 1 is DDC closed. And this second thing follows from the fact that in general, you always have this formula, which relates DDC to the co-differential of theta. And this is in general an important tool, but especially because you can, because of this second condition, you can give a good definition of the degree of a holomorphic vector bundle, even in the context of non-Kähler geometry using a Gauduchon metric. And so you can study stability properties of vector bundles. And another reason why these are very important is because of the famous result of Gauduchon, which shows that if the manifold has real dimension bigger than 2 and is compact, then any conformal class of almost Hermitian metrics has a unique Gauduchon metric in this conformal class, well, unique up to multiplying by a positive constant. And so we, in our paper, we addressed one or two questions. So we wondered if we could express the special classes of metrics, of Hermitian metrics, as extremals of some functionals, eventually, if possible, unique. And more generally, whether we could find some other classes, maybe of interesting Hermitian metrics, appearing as extremals of some natural functionals. And these questions are not new. Paul Gauduchon and Weissman already considered two such functionals in the following context. So they suppose that the manifold was compact and complex. H1 denotes the set of all Hermitian metrics of total volume 1. And inside of H1, you can look at a conformal class of Hermitian metrics of total volume 1 as well. So Gauduchon considered the functional given by the L2 norm of the Lie form, and Weissman looked at the functional given by the L2 norm of the D of the Lie form. So Weissman looked at this because he was hoping that, actually he only looked in complex dimension 2, in the hope that the critical points of this functional might be the locally conformally Kähler metrics. In any case, it's clear that locally conformally Kähler metrics are critical points of this. However, he was not able to show that. On the other hand, in complex dimension 3 or bigger, then it's easy to see that the only critical value of this functional is 0. So all the critical points are only locally conformally balanced metrics. And yeah, in complex dimension 2, this functional is conformally invariant. Gauduchon looked at this functional in general, and he computed the Euler-Lagrange equation for both the functional view on H1 and also viewed restricted only to a conformal class. And in complex dimension 2, he obtained that the only critical points of this functional on the whole space of Hermitian metrics is given by only the Kähler metrics. When you restrict this functional on a conformal class, new critical points appear, in fact, but there is no general existence and uniqueness result for this on conformal classes. And we consider the following functionals, but restricted to a conformal class. a normalized conformal class. So the first one is given by the L2 norm of the codifferential of the Lie form. The second one, I will talk about it more. It's the L2 norm of dg theta. And two more, given one of them dc omega, which is the same as d omega, and the other one the dc omega. So I will mostly concentrate on the first two today, in fact, because this is where we found more interesting things to say. So let me start with the first one. So we, as before, the manifold is compact, almost complex, and we fix the conformal class of normalized Hermitian matrix, and we look at this functional. And the first remark is, of course, Gauduchon matrix for which this is 0 are critical points of G. And we showed that if the manifold is compact, then these are indeed all the critical points of G. So first on restricted on a conformal class, but then evidently also on the whole space of the almost Hermitian matrix. And the proof of this goes as follows. So first of all, metric is critical if for any variation up to order 1, the differential is 0. And now a variation up to order 1 has to satisfy that phi, the mean value of phi is 0. dv omega always is the volume induced by the metric. And using the following formulas. So the fact that the Lie form of a conformal metric changes in this manner in terms of the initial Lie form, and the fact that the Hodge star acting on one form changes conformally in this via this formula with respect to the Hodge star with respect to omega. We compute the variation of G, and we find this formula up to order 1. So this means that for any smooth function phi dot which satisfies that its integral is 0 of order the manifold, this quantity has to be 0. So this implies in particular that the colored thing that I had here has to be constant. And this is the Euler-Lagrange equation for a critical metric of this functional. And now we can go further, in fact. So first of all, we can detect the sign of this constant by integrating this quantity over the manifold. So this, of course, will be 0, and d moves here, so we obtain this part. And then we obtain that this constant has to be 0 or positive. And then you look at the minimum point for the function d star, where the Laplace operator has to be negative or 0. And then we obtain that on the one hand, the constant is non-negative. On the other hand, it's a sum of two negative quantities. So this is less or equal than 0, but this as well. And with this, we obtain that d star theta dx0 has to be 0. But recall that this was a minimum point, and the integral of this function is 0. So this implies then the whole function is completely 0, is 0 everywhere. So this means that the critical point, so a metric satisfying this equation, has to be Gauduchon. So this concludes the proof of the first result. And next I will discuss the second function. So before discussing the functional, let me say a few words about the quantity that appears here. So this form dg theta. So I will restrict myself to the case of when the complex structure is integrable, just for the motivation. First remark is the following, is that this form is 0 precisely when the metric is balanced on a compact manifold. And this is because by definition, this is equivalent to dd star of omega is 0. And then after integrating on the manifold, you obtain that omega is co-closed. And then you obtain that the Lie form is 0. A second remark is the following thing, is that once you fix a metric on a complex manifold, you have, in general, if the metric is not scalar, you have two natural Hermitian connections on the tangent bundle. The first one is the Chern connection, which is the unique Hermitian connection whose 0-1 part is the Cauchy-Riemann operator. And the second connection is the so-called Bismuth connection, or the Keller with torsion connection. And this is the unique connection, which is Hermitian. So these are the two conditions saying Hermitian. And the third condition is that it has totally skew-symmetric torsion. And these two connections coincide precisely when the metric is scalar. So in general, on non-scalar manifolds, they both induce Hermitian connections on the determinant line bundle, and their curvatures of this on this line bundle differ precisely by this form digitata. So in some sense, digitata represents the curvature defect of not being scalar in some sense on this determinant line bundle. So this is why one instance where this form appears. Another instance is when we are in the locally conformally scalar or locally conformally balanced case. So suppose that the Lie form is closed, then it has the Durham class, and as such, via the universal coefficient theorem, it determines a homomorphism from the fundamental group to R+. And so it defines a flat line bundle. It's actually, it defines even a real flat line bundle, but then you can tensorize it by C and you have a holomorphic flat line bundle. And it's related to the metric in the fact that the conformal class can be seen as a section of the symmetric endomorphisms of symmetric forms on X valued in this line bundle. So this is the weight line bundle of the conformal class. And as soon as you trivialize this line bundle by choosing a representative of the Durham class, you have a natural Hermitian structure on this line bundle. And then you have the Chern curvature of the induced Chern connection corresponding to the natural holomorphic structure and this Hermitian structure. And this Chern curvature is, again, precisely this form. And in these two situations, this is an important invariant because although this line bundle is topologically trivial, so it has real first Chern class 0, it will, in general, have first both Chern class non-zero. So this form, although it's D exact, it is in general non-DDC exact in the case of strict, locally conformally scalar and balanced metrics. Okay, so the first thing we did in the same manner as before is that we computed the Euler-Lagrange equation of this functional on a compact almost complex manifold, but this functional restricted to a conformal class. And this is the equation. So in the general case, we did not say anything about it, but we restricted to the case of dimension 2. More precisely, we also suppose that the complex structure is integrable and the complex dimension is 2. And in this case, we can show that any conformal class of normalized Hermitian metrics admits a unique extremal metric for the functional f. And moreover, f of omega minimizes this functional. And it's not necessarily 0. So I will talk about the proof of this result, but first let me say something else. So unlike the first functional, G, the critical points of f restricted to omega 1 will no longer be critical points of f on the whole space of Hermitian matrix. And this is because we constructed, in fact, matrix. We showed that on a Inouye-Bombieri surface of type Sm does not matter what it is. It's just a compact complex surface, which is not scalar. So there exists a family indexed by R of Hermitian matrix of total volume 1. so that the functional on this evaluated in this each of these metrics tends to 0. And each of these metrics minimizes F in the corresponding conformal class. But so this in particular shows that the infimum on this functional of the whole space of Hermitian metrics is 0. But however, this 0 cannot be attained, because if F of some metric would be 0, this would mean that dg theta would be 0. I already said that this would imply theta is 0. And since we are in complex dimension 2, this would imply the metric is scalar. And these surfaces, however, they have first Betty 1, 1, and they admit no Kähler metric. Okay. So let me start with the proof of this result. So first of all, by the equation that I showed before, in complex dimension 2, it simplifies to this equation, which is also equivalent to this equation, and then to this equation. So we have to solve this equation. And again, using the fact that the dimension is 2, we can express a star of dg theta as this is the trace of the form times omega minus its 1, 1 part plus its 2, 0, 0, 2 part. And furthermore, we have to apply the dc to this quantity. But now we look at the fact that as the complex dimension is 2, this has to vanish. As the dc of dg theta has to vanish, this implies that also the 1, 1 part is the dc closed. So all is left here is only this part. So we find that omega is critical for F in complex dimension 2 when this equation is satisfied. So in order to show our theorem, we have to show that in any conformal class, their existence is unique, such a metric satisfying this equation. And in fact, we did more than this. We looked at a more general setting. So again, we forget about integrability of the complex structure. We suppose we are in a compact manifold, even almost complex structure. And we define the notion of metric, called it distinguished, if this equation is satisfied, where f omega is the trace of this form. So note that when n equals 2, this is exactly the equation that we had before, that we had to solve. And it can be easily computed that the trace of this form is precisely the norm of the Lie form plus the star of theta. And then we showed that even in this more general setting, if the manifold is compact and of real dimension bigger than 2, then any conformal class admits a unique representative, which is a distinguished metric. And moreover, there are two cases that you can distinguish. One of them is when this function is 0 everywhere, and this is, in this case, the metric is balanced. The second case, if it's not 0 everywhere, then it's never 0. This function is strictly positive on x. And in the second case, this equation is precisely, if you know that this is positive, then this is precisely the equation of the Gauduchon matrix. So this is the Gauduchon matrix. And how does the proof go? So first of all, we compute the dc of any function times omega n minus 1. So this gives this formula wedge omega n minus 1, which is then the same as the trace of this formula times omega n. And then you compute the trace of everybody, and you find that this equals this quantity here. And recall that we are looking for a metric which satisfies this. So we want f to the power n minus 1 to satisfy that this is 0. So this means that it has to be in the kernel of this operator. And you can check that its L2 formal adjoint is given by this formula. And what we do is we fix any Hermitian metric in the conformal class. Then L0 and L0 star will denote the same operators, but computed with respect to omega 0. And we first know the following thing. So by the Hopf maximum principle, since L0 has no 0 order term, its kernel is only given by the constants. Then the second remark tells us that we know then that the kernel of L0 also has to have dimension 1 because the kernel of L0 star has dimension 1. And then Gauduchon, when he showed existence of Gauduchon matrix, again using the Hopf-Maximal principle, showed that in fact the kernel is generated by a strictly positive function, even though it's not necessarily constant. So what we do is we have a reference metric omega 0, and if we change it conformally, then we have the following changes of formulas. So L changes in this manner, and F omega changes in this manner, and note that L0 star appears in this conformal change of F omega. So what do we want? Omega 0 is fixed, and so we are looking for a smooth function so that F omega, meaning this quantity, has to be in the kernel of L. Via these two formulas, this means that this quantity has to be in the kernel of L0. And so, since the kernel of L0 is generated by alpha, this means that this has to be a constant times alpha. And rewriting this equation, you find this equation. So this means that we need to have that the quantity on the right has to be in the image of L0 star. But now the image of L0 is the L2 orthogonal of the kernel of L0, which was generated by alpha. So this quantity will be indeed in the image precisely when integrated against alpha, it gives 0. And this also rewrites in this manner. So this determines us precisely the constant k by remarking that this is strictly positive, so we are allowed to divide. So then we know that there exists indeed a solution for our equation if we take k uniquely determined by this quantity. And regarding unicity, we know that any other solution must differ from an element of the kernel of L0, which was given by the constants. So in particular, this means that any two solutions differ by a constant multiple. So if you normalize by the volume, then you have a unique normalized distinguished metric. And for the final remark about positivity, we know that after we solve this equation, we know that F omega is given by this formula. So since this is strictly positive and this is strictly positive, the sign of F is completely determined by this constant. And since the integral over x of this function is positive or 0, then this means that this constant is positive or 0. And so we distinguish two cases. Either this constant is 0, which then means that the function is 0. And after integration, you find that the norm of theta has to be 0, and so theta has to be 0. And this is the case when omega is balanced. Or you are in the second case where this constant is positive, and then this implies by this formula that F omega is positive. And so indeed, this metric will be Gauduchon. So in particular, note that when you are not in the balanced case, we have found metrics which managed to make the scalar curvature of the line bundle that we had, the weight line bundle, strictly positive everywhere or strictly negative, depending on which power it takes. And now since these distinguished metrics, they give unique representatives of conformal classes, it's natural to ask if maybe they are already Gauduchon, because this could happen. And in fact, it does not always happen. So the result is the following, is that omega, so it's exactly what is written here. So any two affirmation of this imply the third. So if omega is both Gauduchon and distinguished, then necessarily the norm of the Lie form is constant. And you do the same. If the norm is constant and omega is distinguished, then it's Gauduchon. If omega is Gauduchon and the norm is constant, then the metric is distinguished. So there exist many examples of metrics when all three things hold. So distinguished coincide with Gauduchon. For instance, Weissman metrics. Weissman metrics being locally conformally Kähler metrics, which have parallel Lie form. And so these are both Gauduchon and distinguished, since parallel implies that the codifferential of the Lie form will be 0, and then also that the norm of the Lie form is constant. And another remark is that if you are on a manifold which has non-vanishing Euler characteristic, then the Lie form will need to have 0 somewhere. And so in general, this will not be constant. And so distinguished matrix will in general not coincide with Gauduchon matrix unless they are balanced. And the proof of this is similar to what we had before. So if theta is 0, it's clear that the free notions are, I mean, if theta is 0, it's clear that Gauduchon coincides with distinguished because they also coincide with balanced, all two of them. So we suppose that the Lie form is not 0. And first, we see that if we suppose omega is Gauduchon, then this trace F is given by the norm of the Lie form. And so we see that omega is distinguished precisely when, we already saw this, precisely when this form is Gauduchon, but because of uniqueness and of Gauduchon matrix in their conformal classes up to constants, this is equivalent to the fact that theta is Gauduchon, is constant. Norm of the Lie form is constant. Conversely, when we suppose that the norm of the Lie form is constant and positive, and we suppose that omega is distinguished, then I recall you that we knew that this f to the power n minus 1 had to be in the kernel of this operator. And this, you can rewrite this formula in this manner. And then you again use a maximum principle. And so here Q appearing in this formula is the codifferential of the Lie form. So you do the same, you take a minimum point of this function. You know, because we are in this hypothesis, you know that the function of this f is strictly positive at this point. So then you find that since x0 is the minimum point, this is negative or 0, this is positive. So the whole thing is less or equal than 0 on the left-hand side. On the right-hand side, this is 0, this is 0, so you are only left with the other quantity. And so since this is strictly positive, this implies that Q of x0 is positive or 0. And again, since the integral of Q over the manifold is 0, and x0 was a minimum point of Q, this implies that this function vanishes everywhere. So again, omega is Gauduchon. So this concludes the proof of this last remark. And finally, so for the last functionals, there is not much to say. So one of them was given by the L2 norm of DC omega. So one reason why we consider, so this is the same, DC omega is the same as taking the L2 norm of D omega. But we wrote it in this manner because DC omega is also the torsion of the bismuth connection. So this functional is supposed to minimize the torsion of the bismuth connection. And also this is exactly the difference between the bismuth connection and the Levi-Civita connection. And this is the Euler-Lagrange equation for the extremal matrix of this functional restricted to the conformal class, to the normalized conformal class. And of course, you can remark that I already said that Keller metrics are, of course, extremal metrics of this. And the last functional we considered was given by the L2 norm of the DC omega. So, of course, as strongly Keller with torsion metrics are minimizers of this. And we again computed the Euler-Lagrange equation, which is given by this formula. And here there is only one remark, is that when the dimension is 2, then as I already gave you another formula, in fact, this will be a constant multiple of the codifferential of the Lie form. So this functional will then coincide with the initial functional, and so in dimension 2, the critical points of this function are precisely the Gauduchon matrix. And this is all. I stop here.
Thank you. Thank you very much. So it's time for questions. Yes. Are there some questions from the audience? Please ask. I have a question, actually. You mentioned that this function, or the function of f, I think, when you consider it on Bombieri-Inoue, globally you get 0. And you don't have critical points among all the Hermitian normalized metrics. Do you expect this phenomenon to be general on surfaces, on other class 7 surfaces, or you can have it bounded strictly from above something positive?
I don't know. Okay. I don't know what to say. I don't know. In this case, it was just easy computations, but I cannot say. This is also a special example because it's locally homogeneous. So we only worked in with invariant things here. But I don't know in general. I can put the slides.
Okay, yes.
Yeah, but I don't know in general what to expect. We didn't actually think about this. We only rather stumbled upon this example and realized that it holds.
Okay.
Another thing here is that these examples, they all have the same Lie form, for example. And they are all LCK metrics.
Yeah, I understand. You use I guess, the homogeneous structure of them.
Yeah.
Okay, thank you very much. Let's perhaps, if there are no other questions, let's thank the speaker again with reactions. I guess that's the proper way to thank you.